Good day everyone, I am Wayne Matthew Dayata and in this video I will be presenting my deep learning video review named Deep Learning in COVID-19 Detection where the model predictions valid, which are based on two papers, namely AI for radiographic COVID-19 detection, select shortcuts over signals published in 2021 and achieving multi-site generalization for CNN-based disease diagnosis models by mitigating shortcut learning published in 2022. So for our objectives, first, we discuss the need for explainable AI in medical imaging. Second, discuss how explainable AI methods detect and verify shortcut learning. Third, discuss the presented strategies to mitigate shortcut learning. And lastly, provide recommendations for better practices on dataset preparation and deep learning model validations for chest X-ray imaging. Let's begin with our introduction. So, a lot of deep learning models have been developed for medical imaging already, especially in chest X-ray classification studies on the height of the COVID-19 pandemic, with the aid of providing faster solutions for COVID-19 diagnosis in patients. Now, existing studies focus on increasing the accuracy but ignoring the aided interpretation of the model's output, meaning there were a lack of visualizations and interpretations for people to understand the interpretations, the methodologies, the predictions of the deep learning models. So, practitioners and clinicians must be able to understand the model's behavior in a similar manner to their robust clinical procedures before formally adopting the deep learning solutions. This is where explainable AI techniques come in. They can be applied to evaluate both the dataset and the model's validity. So, four other purposes are mentioned. Justify the validity of the model and its predictions through all the visualizations and explanations. Control by mitigating all the confounding factors, also known as shortcuts. Improve. Improve the training methodology, the data preprocessing, data creation, basically the entire pipeline for presenting the deep learning solution. And discover if there are any hidden features and patterns that humans may not recognize, which are also not shortcuts or irrelevant features. Now, this diagram explains the trade-off between model interpretability and performance. So basically, on simpler models just like rule-based learning, where there are clear guidelines to predict a data for one class than another, and when it comes to deep learning and all other complex methods, this is where they are not really interpretable or explainable, and studies are now ongoing to develop methods where all those sophisticated models with high accuracy has their explanations to make sure that there are no confounding features that are being learned. Now, for technical background, we move to all the relevant concepts, including computer vision itself and the methods for explainable AI. And we start with convolutional neural networks or CNN, which is the most common type of neural network for image classification studies. So these are inspired, of course, by the animal visual cortex, where we represent spatial features using various neurons and other layers such as convolution, pooling, etc., down to the usual fully connected and the classification layers. So these matrices are represented using kernels that slide along the input image to capture spatial information, which typical MLPs or multi-layer perceptions will not be able to do so due to the computational complexity. Next, we move on to the methods of explainable AI when it comes to image classification. Now we begin with GradCam or Gradient Weighted Class Activation Map. So to make this straightforward, it uses forward propagation and gradient computation to analyze from the last convolutional layer to the fully connected layer which parts of the pixels, which pixels contribute much to the classification. Example, the face of the dogs and the cats. So when you sum up the computations for each channels, you get the heat map activation for that particular class. Then we move on to saliency map. So unlike in GradCam, um, the visualizations are more clearer down to the edge level, unlike in GradCam that it just shows you large regions. Why? Because it uses guided back propagation to give you as much clearer resolutions compared to GradCams. So to reduce the noise, ReLU is utilized to clip all the values that are less than zero, and it should be accompanied with GradCam, whose heat map is upsampled with bilinear interpolations. Lastly, we have CycleGAN or Cycle Generative Adversarial Network, which solves the image-to-image translation problem. So as you can see in the figure, we don't have to train its paired images, but rather we analyze the features of each class to make the network able to transform the images from one class to another, just like from horse, you got a zebra, from zebra, you got a horse. So as mentioned, you don't need paired input-output images because it is handled in an unsupervised manner using the images that you collected from each class. So that's what we call object transfiguration. So now we're done with the introduction. Let's move on to the first paper discussion. So as mentioned, it was um, written and proposed to counter the issue of shortcut learning and the lack of explainable AI in the previous studies, which is done through external testing across datasets, using saliency maps, and swapping of lateral data markers via CycleGAN. So for the experimental approach, first we reconstruct the different kinds of datasets which will be shown, model training and testing, investigation of model results using explainable AI using saliency maps and cycle GANs, which will be elaborated later, and all the data manipulation experiments that follow to verify the hypothesis of shortcut learning. So again, in the first paper, it's more on an exploration to verify that shortcut learning exists, which is followed by the second paper that explains the techniques to mitigate shortcut learning. So here's the overview of the study design. So as we see, um, the data sets are being separated to simulate internal and external testing. And here is how saliency maps and generative models are like. Saliency maps basically show where it's being focused on the image to generate predictions, while this cycle GAN is where these features, most if not all, that are found in the saliency maps to swap to represent a different class. And here this figure shows the composition of the data set, and below shows a visualization of how internal and external testing has been achieved. So per data set, it's being separated to train and test. And for the test, both the ones from the original dataset and the ones from the new dataset are being used to evaluate the different neural networks. So for model architecture, DenseNet 1-to-1 is used, which is pre-trained on ImageNet using mini-batch stochastic gradient descent, batch size of 16, momentum zero point 0.9, learning rate of 0.01, which is divided by 10 every 5 epochs for 30 epochs. And other networks are being also experimented aside from DenseNet 1-to-1 as comparison, which we will elaborate later. Now, for the data set, the first data set and the second data set, as we see, have two different repositories. So it has hundreds of thousands of radiographs. And for the data set 3, which will come in late into the research, is one that come from the same hospital and over the same time period, emphasizing the need to collate data from the same source and also on the same time period to make sure that while training, it is the model learnings are not done by shortcuts. And as a final note, all images of any given patient are belonging to only a single fold, meaning there is no data leakage. Then for the interpretability approach, here are the formulas for the saliency map construction and for the cycle GAN. So as mentioned in the technical background, saliency maps show what areas of the image give your prediction, and cycle GAN is how it identifies features and transform images from one class to another. Next, we move on to the results. So this is basically the internal and external testing results from their proposed model. So as we can see at first glance, there is a large generalization gap. By generalization gap, we mean the difference between the metrics from internal testing, which is 0.99 to 0.76 if you train in dataset 1 and test in dataset 2. And even if it's vice versa, we still get a huge amount of generalization gap. And when we do it with other neural network architectures, just like the previously researched COVID-19 net and dark COVID net, by the way, these are from published papers, and they unfortunately only tested internal validation, which has been exposed here in the two sets of data sets that there is still a huge discrepancy of the test results. And for CV19 net, this is coming from our paper. It also ensembled the Bayes dense net one-to-one network. So as we see, there is still a huge gap even if ensembling has been employed. Moving on, we summarize the results of the model evaluation phase of this research. So again, there was a high generalization loss because of the difference in performance. So with those results, it suggests that we did not learn properly. Perhaps we look for other things in one data set that was not present in the second data set. What can it be? Possibly shortcuts, possibly confounded factors, which we will be looking for using explainable techniques on why the model was not able to do well in a certain data set, even when it is trained well. So more complex models again does not mean better performance as shown earlier. And now we will be focusing on number 3, which is the identification of spurious confounders. So we pick 3 images and their equivalent saliency maps. And from there, we already clearly see that there are areas outside the lung regions that are being focused and emphasized, just like this: corners, 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 etc., and even below the lungs. So now we know that some of the time, if not most, the models relied on those kinds of shortcuts. Now, after the usage of saliency maps, as mentioned, we use cycle GANs to transform COVID-19 negative radiographs to resemble positive samples and vice versa to capture a broader range of features. So take note again, this process is being automated, and as indicated by the blue rectangles, these markers are being swapped successfully. But again, even the laterality markers marked by the red areas are also being transformed as well. Even the ones with annotations are being interchanged. That means shortcuts were included. Next, this is another representation of the saliency map from the original image to their transformed images using GAN again. So as we can see, the points of emphasis are also moved together. Example, the labels, the R. And for letter B, the researchers tried moving the shoulders because originally it's being identified as a confounding factor, which is around the corners. And true enough, this also got included when they classified the image as either positive or negative, which is completely out of focus. As you see, the lung content was not really included. So their attempted solutions is to modify the dataset and even reconstruct it. First, they did center cropping, but as resulted, it was not statistically significant. Their external validation results gave an AUC of 0.76 prior to cropping and 0.79 after cropping. So they hypothesized tendencies in shifting to other shortcuts, such as the size of lung fields, scapular shadow, size of the cardiac silhouette, image intensities, and the like. So their second solution to try to um, fix this shortcut learning problem is the dataset reconstruction. So what they did is they utilized the third dataset as the training set. So in the third dataset, all positive and negative samples came from the same hospital, the same time, the same environment. So as a result, the researchers found out that there was minimized attention to previously identified shortcuts. Let's look at the visualization. So again, trained with old dataset, trained with new dataset, and tested against dataset 1 using external validation. And now we can see as long as the dataset itself between the two classes does not have any shortcut features, just like the old batches to BIMCV, there are a lot of dataset related gaps that are present in one and absent in the other. So comparing, we have the external validation results in the old network, which is zero point 0.7 compared to zero point 0.8 using the reconstructed dataset, which showed a zero point 0.1 improvement when externally validated against the same dataset 1. And here is another visualization. So here is the dataset 1 test images. Here is the saliency map generated by the dataset 2 tested trained network and the ones trained with dataset 3. So as we notice, there are a lot of check marks symbolizing the improvement in the focus of classification. So as we see, it now focus on the lung contents. Although there are still a few exceptions wherein the corners are or shortcuts are still being utilized, and the most obvious improvement is in this image wherein from dataset 2 it was classified through a shortcut, but then in dataset 3 it was now predicted properly using the lung content. So discussions and insights. So previous studies, they have audited their COVID-19 models, however, were just on 1 to 3 samples and images, which are obviously not enough to generalize that or prove that there was no shortcut learning. Probably a lot of images were being omitted for better presentation purposes. So for future work, of course, they suggest future researchers to do population or at least sample level explanation to justify that there's no shortcut learning and then the model was being properly learned. And of course, other recommendations such as improved collection of training data and improved choice of the prediction task to involve more clinically relevant labels. Now let's move to our second paper, Achieving Multisite Generalization by Mitigating Shortcut Learning. So this is more on the extensive methods now to improve the dataset processing to come up with a model that has less tendencies to shortcut learning. So for the experimental approach, still the same as the first paper, this time with an initial evaluation prior to applying the pre-processing experiments and doing the performance comparison before and after the adjustments. So here is the overall workflow. Then after curating the data, there are now 3 proposed steps in the new preprocessing pipeline, such as lung field segmentation and cropping, histogram equalization, and noise base or other augmentation such as Gaussian noise prior to training and also testing. So take note, there is still external validations as our purpose of deep learning studies is to make sure they generalize well before being deployed to actual clinical environments. Now we have the dataset sources. So although fewer in amount of images, this paper tries to make sure they get as much as diverse images and sources as possible. So different formats, different settings, different hospitals, and even different countries. So for the model architecture, this paper used ResNet 50 with the hyperparameter. So instead of the original image let layers, it was changed to global average pooling, 64 unit fully connected layers, resulting to 184,000 trainable parameters. It applied cosine annealing cyclic learning with max learning rate of 0.0001, trained for 1,000 epochs, and it made some general data preprocessing steps such as conversion to 8-bit PNG, normalization, and channel duplication. It made some minor rotations and also horizontal flipping. Now, here is the architecture. Again, this is the pre-trained part and this is the added part from global average, etc. Evaluation approaches still with the ordinary performance metrics, but there is a drop off. So this means we evaluate these metrics from the internal data, or what we call as seen data, and external validation, or on unseen data. So seen minus unseen gives you the drop off. So after that, techniques to reveal the confounding factors, which is through GradCam. So GradCam, again, computation of importance weights to gradient scores with respect to feature maps of a convolutional layer to generate the class discriminative localization map, or the heat map of L, with the formula given below. Again, for the generalization test or external validation, there is still an internal validation, which is 20% of the seen source and the rest of the um, other sources, which is not being exposed to the model. So what are the confounding factors that are there? First, we have presence of medical devices, which is present in the CCCXRIP dataset. So basically, all the positive cases had devices while all the negative cases don't, just like ventilation equipment or ECG cables. Now, take note, going back to the real scenario, COVID-19 patients were usually bedridden and they are already given life support because they are already in their extreme situations with regards to their respiratory functions. So that is why when these cables are included, unfortunately, they're also incorrectly accounted for in the deep learning models. How? Since the difference was very obvious in the internal dataset alone, that internal testing accuracy was suspiciously high. And the more we can see it in external testing, because for COVID-19 positive sources that do not have devices, there is a very low accuracy. Conversely, for COVID-19 negative sources that also had um, devices with them in the radiograph, there is also a very low accuracy, as highlighted here. So GradCam images confirm that these medical images were incorrectly treated as shortcuts that accounted for during the training. Next, we have both classes from the same source. So very similar to the first paper's observation, as long as you have trained your data on a common environment, just to make sure there are no external dataset related differences, such as the difference in the presentation, or even annotations, or medical devices, or any other irrelevant confounding factors. So for scenario 1, when both use BMCV, which is the same as dataset 3 in the first paper, um, the internal and external results are very, very similar. External results, again, when tested against other dataset. In the second scenario, wherein the positive and negative classes come from different datasets, obviously, the learning was better because of all those shortcuts, and as a result, it was not able to generalize, it was not able to scale, hence giving the 0.43 generalization gap, which was, of course, undesirable. Now, what are the preprocessing techniques that are used? First, we have lung segmentation and cropping, uh, basically to eliminate the markers present at the edges. So with this was not manually done, but rather they took a pre-trained UNet model, which was trained on one chest X-ray dataset to perform lung segmentation on its own. So as we see in the GradCam results, the model now shifted from all those lateral shortcuts and annotations to the actual lung contents to learn from the medical features themselves. So what are the results? Again, automatic lung segmentation with UNet. So when they tested the change in results using McNemar's p-value test, it resulted in 0.02, which indicated a significant performance increase. So there was improvement in both internal testing 0.92 to 0.96 and external testing with accuracy 0.54 to 0.57 and AUC 0.53 to 0.59. But however, if you see these values, They still did not reach 60%. That means there is a lot more that we have to do. So the researchers propose a second preprocessing pipeline, which is histogram equalization. So if we notice, um, these are examples from two data sets, the V2 COVID-19 N2 and the patches dataset. So what histogram equalization does is that it is a technique for image normalization that equalizes or standardizes um, the contrast, no, the brightness levels of the pixel to make sure the medical features in the lung content will be more visible and will be clearer, making the model less prone to shortcut learning. And this is what happens after the equalization. So the lung contents are clearer. Whatever was being blurred at the moment is now clearer, making the models learn things more appropriately. What happens to the result? So there is again improvements in internal and external testing, validated also via McNemar's p-value test. So it's still significant. And for the accuracy and AUC in the external testing, it increased from 0.58 to 0.61 and 0.59 to 0.66 respectively, finally surpassing 60%, but obviously it is still not quite enough for a generalization or deployment. So the third augmentation method they did was noise-based augmentation. Basically, Gaussian noise to add high-frequency features to each chest X-ray images. They applied this with zero mean and standard deviation of 0.01. So original and augmented image are mixed together in training data for deep learning models to handle all scenarios and all instances to make sure that there is no overfitting, there is no shortcuts, minimized shortcuts, I mean, that are being learned. So as a result, this is what happened. So prior to noise augmentation or Gaussian blur, um, there is a huge generalization gap represented by the blue and the yellow colors. So right after augmentation, although there is a decrease in the internal validation scores, there is an increase in the external validation scores. So it doesn't matter in the training as long as during the testing and the external validation, it yielded a higher result. So finally, it surpassed 80%. So as we can see, these are accuracy values. So from the baseline, it's just 0.72. It increased to 0.81. And the gaps between the internal and external results reduced from 0.20 to just 0.09, which is very, very significant. So if you use higher or lower STD values, as we can see, even if it's zero point 0.1 here, but then the overall accuracy is still lower than the 0.01 STD value. So before going to the discussion, this paper made a highlight by referencing to a previous study, Deep COVID XR, which is an ensemble of 6 convolutional neural networks with inputs consisting of crop and uncropped images of 2 downsampled resolutions. They, similar to the um, first and second papers, they gathered data from multiple sites and tested using an different environment which was not exposed to the um, original trained data. However, it was mentioned that it was still from the same healthcare system, so with the same equipment, um, which according to the current paper, they said that there is still tendencies for shortcut learning because um, of the shortcuts learned during the training data set, which does not scale out. So how? In their results, they reported 83% accuracy and 75% sensitivity. But then when the researchers in this paper replicated the study, they got a lower sensitivity value of just 58% compared to 75%. So for the final discussions, we have 3 points. So impacts on certain processes. So larger data sets, ensembles, or model complexity are irrelevant, as we can see in the first paper and the second paper. Um, Both exhibited not so high external validation scores. So it suggested that the problem should be on the dataset or the model training process. But for both papers, it was focused just on the dataset pre-processing. So long segmentation, histogram equalization, and Gaussian noise were the added steps in the new pipeline, which lowered the performance drop from internal to external validations from 20 to 9%. So other recommendations involve multitask learning, few shot learning, semi-supervised learning, and attention models, which all give you abstract feature distillation, which is another way to mitigate shortcut learning. But the process behind it perhaps is more technical and more costly. Therefore, there is still minimal studies with regards to healthcare imaging. And obviously, model level recommendations, so better explainable AI solutions, and more complex loss functions to eliminate the learning of irrelevant shortcuts. So to wrap up and summarize, here is the summary. So for both papers, they use multiple dataset sources, wherein the second paper has more diverse sources but way more fewer images from the first paper. But nonetheless, they arrive at the same conclusion that shortcut learning exists and shortcut learning is very inevitable because of the nature of the datasets used. So for the base models, the first paper used DenseNet 1-to-1 together with other ensembles, while the second paper started from ResNet 50. So for the XAI methods, the first used saliency maps and cycle GAN, while the second used GradCam. Improvement methods, the first paper used center cropping and um, improved data selection, while the second paper proposed the new data preprocessing pipeline. For the first paper, the outcome was an increased external validation accuracy on the same validation set from 70 to 80%, while the second paper reported a reduction of performance drop from 20% to 9%. So other findings for the first paper, not all shortcuts generalize, and auditing must be done on population level or at least on the sample level instead of just 1 to 3 images. And for the second paper, complex models are still more prone to shortcuts as mentioned in the Deep COVID XR comparison. And to wrap it up, um, we need to focus quality over quantity whenever we do deep learning studies, um, regardless whether it's in the pre-processing, on the model selection and training, or even with the outcome explanation. It's not about how high is our accuracy, how much data we have, or how complex our architecture is. But what's more important aside from efficiency is explainability, because now exposing that shortcut learning is evident in a lot of deep learning studies which are overseen by a lot of researchers. It shows to us that we need more advanced validation and visualization methods to make sure that not only the people are able to learn the process behind the predictions of the AI models, but most importantly, that the process and the features identified by the AI models are consistent to the um, medically identified features in clinical studies. So that will be the end of our presentation, and thank you so much for listening.